So let's talk a little bit about electrical potential energy and kinetic energy. So we talked about electric potential, which is voltage, but electrical potential energy is just potential energy that's electrical, as opposed to, say, potential energy that's gravitational. And so we might say that we already said that potential energy is the charge times the voltage. And so, for example, we can have a charge that's at a high voltage, so we can say PE initial is equal to QV, whatever our voltage is at, and then PE final is equal to 0. This is a charge that starts at a high voltage and then is released and runs down to a low voltage, and so the change in potential energy is just the charge times the voltage. That might be a Coulomb times 12 volts or something like that, right? And if it starts here at stationary, we can say its initial kinetic energy of the charge is equal to 0, and final kinetic energy is 1/2 mv squared. So let me just give you an example of this. We can have two plates here, say, that are connected to each other by a battery. By the way, this is the generic drawing of a battery. So this is the plus end of a battery, and this is the minus end of a battery, typically called ground. And I'm just attaching it to a metal plate. These are just like we saw, and so they're like this, right? The wire's connected to them, it's a conductor, and so it's like the wire's connected all over. And so we would say this is at 0 volts, and this is at V, and this is a whatever, a 12 volt battery, let's say, or something like that. Doesn't matter. And so just let me say a few things about this. This typically creates a uniform electric field. Since this is the positive plate and this is the negative plate, electric field lines will point this way, right, like this, across here. If I release a positive charge here at the high voltage end, let me just write it this way, Q greater than 0, this charge will be pushed across to this side, right? If the electric field here is E, then I would say F equals QE, right? And then I would say the work done is just the force times the distance, which is Q times the electric field times the distance, where that is the distance. And so the work done by the electric field pushing the charge across here is just the force that's applied. Remember, E equals F over Q. And so the charge is just pushed across here. So it has a high potential energy. It's got a positive charge, and so it doesn't like to be next to the positive plate. It gets pushed across, work gets done on it. So we can apply conservation of energy to this, and we can say, look, KE initial plus PE initial equals KE final plus PE final, right? Or we can say KE final, if you rearrange that, minus KE initial is equal to PE initial minus PE final. So I move the PE to this side and the KE to that side, and I get this. Well, the initial kinetic energy was 0 because we said the charge was stationary, and we said the final potential energy was 0. And so what we get is 1/2 mv squared is equal to QV, where V is the voltage across there, right? And so if we know the voltage and the charge and the mass of the particle, we can calculate the velocity. We can say the velocity is equal to 2qv over m square rooted. So so I can just make up an example of this, and I can say, well, assume I'll leave that guy there, right? So what is the final velocity of proton if the voltage is 100 volts? And so we get the velocity is the square root of 2 times the charge on a proton, which is 1.6 times 10 to the minus 19th coulombs times 100 volts, which is 100 joules per coulomb, divided by 1.67 times 10 to the negative 27 kilograms. Right, and notice that that kilojoules is kilogram meter over second squared, and so the kilograms cancel, these two coulombs cancel, right, and I get a velocity of 1.38 times 10 to the 5th meters per second. So let's talk about these parallel plates again. I want to use them to relate the electric potential and the electric field for parallel plate systems. This doesn't apply to all systems. Like point charges, we'll have something different for that. But if this is the positive plate, right, we know it's the positive plate because this is our long end of our battery, and so that's the ground plate, and so we can say this is our positive end and this is our negative end. And so you might remember that the definition of work is equal to force times distance. We usually have a cosine theta here, but for now we'll assume that the force is in the direction of motion just to keep things simple, right? And so for an electrical system, the force is the charge times the electric field, and then that's what the force is times the distance, and so the work done is is the charge times the electric field times the distance, moving a charge from here to here. But you also might remember that the work done is minus the change in potential energy. And so if I drop a ball off a cliff, the gravitational field is pushing the ball down, and so the gravitational field is doing positive work because the ball is going down and it's being pushed down, but the potential energy is decreasing. We always want potential energy to increase when you're doing work against the field, and so that's the way it's going to work here. If you remember, this is minus the change in the minus Q times the change in voltage, or we'll just say that the final voltage is 0, so we'll say this is minus Q times V. And so if I relate these two, if I say, look, minus QV is equal to Q times the electric field times the distance, I can cancel the Q's, and I get the electric field, let me just solve this way. And so it's the voltage over distance is the electric field, and so it's often written as volts per meter is the units. If you remember, we've already seen, since the electric field in other situations was the force per charge, it's also sometimes written as newtons per coulomb. Those two are actually exactly the same, because a volt is a joule per coulomb, and a joule divided by a meter is a Newton, so this is the same thing as this one. So what does that minus sign mean? Right, let's talk about that for a second. If you remember, the electric field points in the direction a positive charge will go. And so this is the 0 volt end, and this is a higher voltage end, right? And so what it's saying, the minus sign saying is, look, it doesn't point towards the high voltage, it points away. It points from high voltage to low voltage. And that's the direction a positive charge would go, right? The higher your potential energy for a positive charge, the higher your voltage, and the electric field points away from that because it points in the direction a positive charge wants to go, which is down. Same thing with gravity. Most of the time, we'll just be dealing with magnitudes, because if I drew a positive plate and a negative plate, you would already know that the electric field is going to point from the positive charge towards the negative charge. So most of the time, we'll just be asking for the magnitude of the electric field. But this is a relationship between electric field and the voltage for parallel plate systems. So we're going to calculate the maximum possible voltage between two plates. Right, so I have two plates here, and I'm going to put a battery in there again. Right, and I want to know what's the maximum I can get in here, and it turns out there is a maximum. You may notice every once in a while you walk across the carpet and you'll touch a doorknob, you'll get a spark. If I get a voltage high enough, if this is air in here, then I'll get a spark. And it turns out that what happens is electric fields that are large enough will cause charge to flow across the plates. Technically, the charges flow from negative to positive because it's electrons that are leaving, and thus neutralize the plates. And so it turns out that the maximum electric field air can handle is it can handle 3 million volts per meter. This is about 30,000 volts per centimeter. And this means if you get a shock, a spark off a doorknob, where the spark jumped through the air and it was about a centimeter long, you received a 30,000 volt shock. Now you may say, well, why doesn't that kill me? The answer is because the charge is really tiny. So it'd be like sticking your hand out the window of your car while it's driving and getting hit by a moth at 70 miles an hour. It doesn't really do much damage. If that was a baseball or a bowling ball or another car at 70 miles an hour, it would do a lot of damage. But this tiny amount of charge isn't that big a deal. And so we can say we're going to ask the question, what is the maximum voltage possible on two plates that are separated by 2.5 centimeters, right? And so I can say, well, Vmax is just Emax times the distance, right? We've already said that E equals V over D, technically minus, but its maximum is just the magnitude of that. And so this is 3 times 10 to the 4th volts per meter times volts per centimeter times 2.5 centimeters, which is 75,000 volts. It's a tight fit there.